where we picked off from last Tuesday, talking about the binomial theorem. The binomial theorem is used to expand your two terms that are added together, so like a plus b, when they're raised to some power. So I'm noticing the really hardcore brightness right here, but okay, you can see it now. Binomial theorem is as follows. Like I said, a plus b to the n for any power is equal to sigma notation, which means the sum, where you perform the following terms from 0, or whatever you set your k to, all the way to n of a to the n minus k, with k starting out at 0, so a to the n for the first one, and b to the k. All right? This is for any n greater than 0 integer. So that's what this funny z right here means. This z is the notation for the set of all integers, right? So any n, that's an integer. Negative 0, 1, 2, dot, 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 etc. Okay. So let's look at an example that we're already familiar with. Let us look at a plus b squared. So we already know what this comes out to. We've done it last time. It tells us in our notes, and it's also one of our identities. Identity 3 or 4. Let's see. Identity, where are you labeled? Identity. Identity 3, yeah. Identity 3 says that a plus b squared is equal to a squared plus 2ab plus b squared. Now, according to tradition, we would do this by taking a plus b and multiplying it by a plus b, the old-fashioned way, where you say, okay, a times a is a squared. You can't really see that orange, I see. You say a times a is a squared plus, all right, a times b, ab, plus b times a, ba, plus b times b was b squared. Then you can combine your like terms ab and ba because you can switch it around. A squared plus 2ab, or ba, it's the same thing, plus b squared. All right, and you may say, well, that's not too bad. Why would I want to learn another method to do this? Well, you'll see a little bit later when we look into a longer example. So using the binomial theorem, a plus b squared, you know that a equals a, b equals b, and in this case, n equals 2. So let's start out when k equals 0, because remember, what we're doing here is this here, this here for k equals 0, then k equals 1, then k equals 2, etc. until you get to k equals n. So when k equals 0, a to the n minus k, n equals 2, is a squared. Times b to the k is b raised to the 0 power, which is just 1. All right, add your next term, a to the n minus k. Well, now k equals 1. 2 minus 1 is just 1. B to the k, b to the first power is just b, plus, now we have k equals 2. a squared is a to the 0 power, or just 1, plus b to the k. And you may say, hey, this is wrong. We only have a squared plus a b plus b squared. We're missing a 2 here. You look at your example right here. Well, that's where our old buddy Pascal's triangle comes into play. And Pascal's triangle was created by a physicist and scientist who needed to find a way to complete the binomial theorem, and that's what it does. It gives us our constants for the binomial theorem. So what is Pascal's triangle? He said, let me start out with the number 1. Well, it's a triangle, so second line ought to be larger than the first. Yeah, it is, but there's always 1s on the outside, so bring down your 1s. Now, there's nothing to add to 1, so there's nothing in the middle here. Let's go ahead, bring down our 1s once again. Now, to find the remainder of Pascal's triangle, I'm trying to figure out this. I guess just when I move that gets brighter and heavier. All right. 1 plus 1 is 2. That's how you find your biggest digit. You can assume that there's zeros on this outside of your 1, right? 0, 0, 0 plus 1 is 1. Here you have 1 plus 1 equals 2. So you want to go down to your next part of the triangle. Put your 1s on the outside once again. 1 plus 2, 3. 2 plus 1, 3. 1's on the outside again.